what we have shown basically that if I take the Dirac train, the correspondent Fourier transform has two expressions. One is the sum from minus infinity to infinity of e to the minus j omega n ts, or we have this alternative form p of omega equal the sum, the infinite sum from k equal minus infinity to infinity of 2 pi over ts of delta omega minus 2 pi over tsk. And if we define the sampling frequency, 2 pi over sub ts, this is more like the cyclic frequency with respect to 2 pi. We can rewrite this Fourier Fourier transform as omega s delta of omega minus omega sk. So we see that we have this expression, which is it is basically a Dirac train in omega. Indeed, the Fourier transform now is given by a sequence of deltas which have a strength omega sub s. And it is not a surprise now that these two quantities are equivalent. Indeed, this Dirac train is a periodic function in omega with the period t naught is equal to omega sub s. So what we have here is simply the Fourier series of this quantity here. So this is the Fourier series of the Dirac train. That's very nice. Okay, so of course, I also show you that Pt can even be written as a Fourier series, and is equal to k equal minus infinity to infinity of 1 over t sub s of e to the j 2 pi over ts kt. And this is the Fourier series. And again here now you can see the duality of this particular signal. So we have a Dirac train in time, which has this Fourier transform, and the correspondent, which has this Fourier series, and the correspondent Fourier transform of P of t is also a Dirac train in omega, which has this Fourier series. Okay, and so we can use both the expressions, and I'm going to show you that this expression is convenient. If we want to define the discrete time Fourier transform. Okay. Instead, this other formulation is more convenient for sampling. Okay. Because now we can use these results to compute to evaluate the Fourier transform of the Diractified signal. Because let's go back to our main goal. So we have the continuous signal, we multiply it by the Dirac train, and we get the Diractified signal. Diractified signal. And now, we would like to design a filter, h of j omega, or input or impulse response h of t, which will, and we would like to design this filter in such a way to recover the original signal. But we need to understand what are the conditions under which these things occur, and what is the shape of the filter, okay? And to do that, we need the Fourier transform of this signal, okay? And that's why, now we understood what is the Fourier transform of P of t. We have two forms, and of course now we can use the Fourier transform of P to compute the Fourier transform of the Diractified signal. So here there are two ways to do it. This is basically given by the multiplication P of t, okay? And this has this is also equivalent to what? X of t sum over n of delta t minus nts, which is also equal to the sum over n from minus infinity to infinity of x of nts times delta t minus nts. That's what I already showed you before. And so here we have again two expressions. So I have this product, but I also have the same quantity, the same signal expressed as an infinite sum. And of course, the correspondent Fourier transform, there are two ways to do it. I can do the Fourier transform of this infinite sum, and this is going to give me what? It's going to give me the infinite sum over n of this coefficient times the Fourier transform of this shifted delta, which is going to give me a term e to the minus j omega n t sub s times 1, which is the Fourier transform of a delta. And that is one expression that may be useful or not. We will see now. And then I can also apply the duality property of the Fourier transform and write, and the Fourier transform of a product is equal to 1 over 2 pi the Fourier transform of the original signal x of omega convolved with the Fourier transform for P of omega. Okay? And of course, for P of omega, we have two expressions. We know that P of omega is equal to the sum over n of e to the minus j omega n t sub s, but this is also equal to the infinite sum over k of 2 pi over ts times delta of omega minus omega s times k. And of course, this quantity here is basically omega s, okay? So again, that's what we learned from the previous calculations. Now, this form, these are equivalent. This form is not going to help us too much to design this filter, okay? Because we don't have an understanding of how the spectrum of x sub s of the Diractified signal looks like, okay? This is a very complex form. However, this form, it reminds you of what? Of the definition of discrete time Fourier transform, is right? So, and again, that's, and we're going to discuss it later on, but you see already, you can use this formula basically, to define the discrete time Fourier transform. So it looks like, we need to work out this formulation, okay, in terms of convolutions. But now, when we have convolutions, what is the best way to, what is the best function, what is the easy way to make, what is the easiest convolution that you can do? Is when you are convolving a signal with a bunch of deltas. So now, when I want to do this convolution, for sure, I don't want to use this formulation for P of omega given as a Fourier series. But I want the original signal, which is the original Fourier transform, which is given as a Dirac train in omega. So this convolution now is going to be easy to do if I have a bunch of deltas, okay? Indeed, this is equal to 1 over 2 pi x of omega convolved with, omega s times this infinite sum of deltas. And you can see that I can bring this omega s outside, and actually let me do it more carefully. So we have what? We have that x sub the Fourier transform of the Diractified signal is equal to 1 over 2 pi the convolution between x of omega and p of omega. And now we can use the expression of the Fourier transform of the Dirac train in terms of a Dirac train in the frequency domain. And this is equal to 1 over 2 pi x of omega convolved, open parentheses. Now I have, maybe I keep it as a 2 pi over ts, okay? It's the same, times the infinite sum from minus infinity to infinity of delta omega minus omega s k. And now you can see that this is easy to deal with, because I can bring this coefficient outside the convolution, and so 2 pi and 2 pi simplify, and I'm left with 1 over ts x of omega convolved with the infinite sum from minus infinity to infinity of a bunch of deltas. But now the convolution is a linear operator, so this is equal to 1 over ts, the sum from k equal minus infinity to infinity, x of omega convolved with a shifted delta. But now I know what is the results of a convolution with a shifted delta. This is simply equal to the spectrum x of omega shifted by omega s times k. So you see that the final result is this, that the Fourier transform of the Diractified signal is a periodic function. This is basically x of s of omega. So this is a periodic function. And the period is omega s. And so they are shifted copies of the original spectrum in a sequence, in a train of copies of the original spectrum. So indeed, now let's we got our results here. Okay. Now we can do something, because we show that x of omega, the spectrum of the Diractified signal, is equal to 1 over ts the infinite sum from k equal minus infinity to infinity of the original spectrum shifted by omega sk. So what does it mean here physically, or practically? So how we interpret these results? Okay, we did all this math, but now can we use it to design the filter? Because remember that what we want to do is we have xt, we multiplied by the Dirac train, and we get the Diractified signal. This is the Diractified signal. And now what we want to do, we want to design a filter and pass this signal here, the Diractified signal, and see if we can reobtain the original one. Okay, so now let's see in Fourier space what we have. Okay, let me do it again. Here I have in the time domain, this is t, we have the original signal x of t, and then what do? We did the Diractification, so this is NTS and so on. So this is XS of t. This is the Diractified signal, and the correspondent Fourier transform is the following. So here I have the domain omega. Here I have 0. Now let's try to understand here omega, and let's make every omega s. Let me do it correctly so we can see exactly what's going on. So here we have omega sub s, 2 omega s, 3 omega sub s, minus omega sub s, minus 2 omega sub s, minus 3 omega sub s. Okay? And here the same things, 0, omega s, and so omega s to omega s, and so on. Okay? Then here we assume that we have our original spectrum. This is x of omega, and I have to be careful now. I need to make sure that yeah, the way I draw it is I have to redo it again. Sorry, I made a mistake. Let me redo it again. Sorry. Xs of omega equal 1 over Ts, the sum from k equal minus infinity to infinity of the original spectrum omega minus omega s times k. Let me remind you that omega sub s is equal to 2 pi over Ts, which is the cyclic frequency of the sampling cyclic frequency. And now, in the time domain, here we have the original signal x of t. Then, we multiply by the Dirac train, and we get the Diractified signal, sample every NTS, so this is x sub of t, and the correspondent Fourier transform is the following. This is omega, this is 0, now I'm gonna do it here, 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 and here. So this is omega sub s, 2 omega sub s, minus omega sub s, minus 2 omega sub s. Then here I'm going to do the Fourier transform omega. So and of course, I also have to define the middle points are also important. Because this is what? Omega sub s divided by 2 minus omega sub s divided by 2, and so on. And here we have the same, 0, omega sub s divided by 2 minus omega sub s divided by 2 minus omega sub s, 2 omega sub s, minus 2 omega sub s. Now, I'm going to assume that the original spectrum is going to be within this band, and it has this shape. This is x of omega, and it is bounded, and this is minus omega b and plus omega b. Okay, so it's going to be only non-zero within this band. And then, what is the Fourier transform of the Diractified signal? I simply take the same spectrum. I multiply by 1 over Ts, and then I do multiple copies every omega sub s. So what does it mean? That I'm going to get, this 1 over Ts x of omega. Then I have the same copy, but at omega s. Then I have another one here. Then I have another one here. And then I have another one here. Okay? So this is, for example, 1 over Ts x of omega minus 2 omega sub s, and so on. So you see that I get multiple copies of the original spectrum, and in this case, there is no overlap between the spectra, which means, what does it mean? It means that omega b is less than omega sub s divided by 2. And this implies that the sampling frequency is greater than twice the maximum frequency of the signal. And this is the famous Nyquist criterion to avoid aliasing. And you can clearly see, now, of course, I'm going to do another example in which this condition is not satisfied, and then you will see the overlap of the spectra. But now you see that we have this formulation, this form of the Fourier transform of the Diractified signal is very useful because we can now